Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the common collector amplifier, which is also known as the emitter follower. So this is the basic circuit of the common collector amplifier. And if you look this circuit, then it is very similar to the common emitter fixed bias circuit. But in case of this common collector amplifier, the resistor is connected at the emitter terminal and also the output is measured at the emitter terminal. Now for the AC signal perspective, all the DC sources in the circuit will act as a 0, while all the coupling capacitors will act as a short circuit. That means for the AC signals, the collector terminal will act as a ground, or we can say that it is the AC ground. So here, the input signal is applied between the base and the ground, or effectively between the base and the collector terminal. Similarly, the output is measured between the emitter and the ground, or effectively between the emitter and the collector terminal. That means here, the collector terminal is common between the input and the output side, and hence this configuration is known as the common collector amplifier. Now as I said, this common collector amplifier is also known as the emitter follower, because here the output at this emitter terminal follows the input signal. Now for the DC signal perspective, the emitter terminal will be 0.7 volt less than the base voltage, but the AC output signal will be approximately equal to the input signal, and in fact it will be slightly less than the input signal. So let us understand this thing intuitively. So let's say the input signal is applied at the base terminal, and because of that we are getting some output at this emitter terminal. So at the base terminal there will be some biasing voltage VB, and on top of this the input signal will be applied. And if we see the output at the emitter terminal, then there will be some emitter voltage VE, and on top of this we will get the output voltage. And definitely this voltage VE will be 0.7 volt less than the base voltage. Now if this AC output signal is more than the input signal, in that case at any given point of time, the difference between the base and the emitter terminal will be less than the 0.7 volt. That means we can say that if the output voltage is more than the input voltage, then the voltage VBE will reduce. And from this expression we can say that because of that the collector current IC will reduce. And we know that the collector current IC is approximately equal to emitter current. So because of that the emitter current will reduce, and effectively because of that the output voltage will reduce. So we can say that because of that the output voltage cannot be more than the input voltage. That means in this emitter follower configuration, the voltage gain is always less than 1. Alright, then the question arises, what is the use of this emitter follower or this common collector amplifier when its gain is less than 1? Well, the emitter follower can be used as a buffer because it provides the high input impedance as well as the low output impedance. So let us find out the expressions of this voltage gain, the input impedance and the output impedance of this emitter follower. And for that, let us do the small signal analysis of this given circuit. So for the small signal analysis, we will follow the same procedure. That means we will consider all the DC sources in the circuit as 0, while we will consider all the coupling capacitors as a short circuit. And then after, we will replace the BJT by the small signal model. Now if you see over here, this emitter resistor is connected between the emitter and the ground terminal. So in the AC equivalent circuit, it can be shown like this. And here, the output is also taken at the emitter terminal. Apart from that, here this base resistor and the input signal is connected between the base and the ground terminal, while this collector terminal is connected to the ground terminal. So this is the AC equivalent circuit of the emitter follower. So now, first of all let us find out the voltage gain. So here, this current is the base current, while this current is the collector current, and the current which is flowing through the emitter resistor is equal to the emitter current. So from this we can say that this output voltage Vout is equal to IE times RE, that is equal to IB plus IC times RE. Now here we know that the voltage V pi can be given as IB times R pi. That means base current IB is equal to V pi divided by R pi. And the collector current IC is equal to GM times V pi. That means the output voltage V out can be given as voltage V pi divided by R pi plus GM times V pi times RE. That means voltage V out is equal to V pi times 1 divided by R pi plus GM times RE. Now we know that the R pi is equal to beta divided by GM, right? That means 1 divided by R pi is equal to GM divided by beta. And this term is much less than GM. For example, if the value of beta is 100, in that case, this 1 over R pi is 100 times less than the GM. That means in this expression, we can neglect this term. That means we can say that this output voltage V out is equal to V pi times GM times RE. So now we need to find the expression of the V pi in terms of the input voltage. Now here if you observe, the voltage at this end is equal to V in. So let us apply the KVL equation in this loop. So if we apply the KVL equation in this loop, then we can write it as voltage V in is equal to voltage V pi plus V out. That means voltage V pi is equal to V in minus V out. That means voltage V out is equal to V in minus V out times GM times RE. That means 1 plus GM times RE times V out is equal to GM times RE times input voltage. That means voltage V out divided by V in, or the voltage gain, is equal to GM times RE divided by 1 plus GM times RE. And if we divide the entire expression by the term GM, then we can write the voltage gain as V out divided by V in is equal to RE divided by 1 over GM plus RE. So this is the expression of the voltage gain. Now usually this 1 divided by GM is much less than RE. That means from this we can say that this voltage gain is approximately equal to unity. Apart from that, if you observe over here, there is a no negative sign in this expression. That means here the input and the output signals are in the phase. Now if you see this expression, then this expression is similar to the voltage divider expression. So from this expression, if we draw the equivalent circuit, then it can be drawn like this. That means here the resistor 1 over GM and the RE are in the series connection, and the output voltage is the voltage across this emitter resistor. So here this portion of the circuit is actually the Thevenin's equivalent circuit, which is seen through the emitter terminal. And in fact, using this equivalent circuit, it is easy to find the output impedance. So let us see how we can find the output impedance. So we know that the output impedance is the Thevenin's equivalent impedance, which is seen through the output side. And for that, we will consider all the independent sources in the circuit as 0. That means this input voltage will act as a short circuit. So now this output impedance is the parallel combination of 1 divided by GM and the RE. So this is the easiest way to find the output impedance. And of course, conventionally, if we find the output impedance from this AC equivalent circuit, then also we will get the same result. So for the sake of completeness, let me also show you how to find the output impedance from this equivalent circuit. So for finding the output impedance, we will consider all the independent sources in the circuit as 0. That means we will consider this input voltage V in as the short circuit. And because of that, this base resistor RB will also get short circuited. So now if we see the equivalent circuit, then it will look like this. So for finding the output impedance, let us apply the test voltage Vt and let us find the test current It. And the ratio of this voltage Vt and the It will gives us the output impedance. And to find that, let us apply the KCL equation at this node. So if we apply the KCL equation, then we can write this current It plus Ic is equal to voltage Vt divided by Re, that is this current, plus voltage Vt divided by R pi, that is this current. That means we can say that current It plus Gm times V pi is equal to voltage Vt divided by Re plus voltage Vt divided by R pi. Now here, if we draw this resistor over here, then you can see that here this voltage V pi is equal to minus Vt. That means from this expression we can write it as current It minus Gm times Vt is equal to Vt divided by Re plus Vt divided by R pi. So if we bring this term on the right hand side, then we can write this expression as current It is equal to Vt times 1 divided by Re plus 1 divided by R pi plus Gm. Or we can say that It divided by Vt is equal to 1 divided by Re plus 1 divided by R pi plus Gm. Now as we have discussed earlier, this term 1 divided by R pi is much less than Gm. That means we can neglect this term. That means It divided by Vt, that is 1 over output impedance, is equal to 1 divided by Re plus 1 divided by Gm. That means here this output impedance is the parallel combination of Re and the 1 over Gm. So in this way, we can also find the output impedance from this conventional method. So now let us find out the input impedance. So the input impedance is the equivalent impedance which is seen through the input side. And unlike the output impedance, we cannot find the input impedance from this equivalent circuit, because here this equivalent circuit is the Thevenin's equivalent circuit which is seen through the emitter terminal. Alright, so now let us see how to find this input impedance. So to find the input impedance, first of all let us find the impedance which is seen through this base resistor. Let's call this resistor as the ZB. So here, let's say the voltage at this node is equal to VB, and as you can see, it is equal to the input voltage. And here, the current which is flowing through this base terminal is equal to IB. So the ratio of this voltage VB and the IB will gives us the ZB. And to find this ZB, let us apply the KVL equation in this loop. That means here, this voltage VB is equal to voltage V pi plus VE. That means voltage VB is equal to IB times R pi plus beta plus 1 times IB times RE. Because we know that this emitter current is equal to beta plus 1 times IB, right? So from this we can say that this voltage VB divided by RB, or the ZB, is equal to R pi plus beta plus 1 times RE. That means now the circuit which is on the right hand side of this resistor RB can be represented by this impedance ZB. So if we see the equivalent circuit, then it will look like this. That means now the equivalent impedance which is seen through the input side, that is this impedance, is the parallel combination of RB and the ZB. That means this input impedance is equal to RB parallel ZB. So in this way, we can find the expression of the input impedance. So these are the expressions of the input impedance, the output impedance, and the voltage gain for this emitter follower. Now, so far in our discussion, we have assumed that the output resistance of this transistor was infinite. But if there is a finite output resistance, then these expressions will get modified. That means instead of the emitter resistor, there will be a parallel combination of Re and the R0. Now although the voltage gain of this emitter follower is close to unity, but it provides the high input impedance as well as the low output impedance. That means this circuit can be used as a buffer circuit. And to understand it better, let us take one example. So here we have been given one common emitter amplifier and we have been given that its voltage gain is 20 when there is a no load connected to it. So in the first case, we have been asked to find the voltage gain of the circuit when we connect a 8 ohm speaker at the output. While in the second case, this emitter follower, which is biased at the 5 mA, is connected between the amplifier and the speaker. And in that case, we have been asked to find the voltage gain. So first of all, let us find the voltage gain when the 8 ohm resistor is connected to the amplifier. That means here, this load resistor RL is equal to 8 ohm. Now we know that for the common emitter amplifier, the voltage gain can be given as minus Gm times RC parallel RL. So here RC is equal to 1 kilo ohm while the RL is equal to 8 ohm. That means the RC parallel RL will be approximately equal to 8 ohm. Now here we have been given that the voltage gain of this amplifier is 20 when there is a no load connected to it. That means without the load, the voltage gain can be given as Gm times RC. That means Gm is equal to 20 divided by 1000. So let us put this value of Gm in this expression and let us find the voltage gain when there is a 8 ohm load connected to this amplifier circuit. That means the voltage gain AV is equal to minus 20 divided by 1000 times 1 kilo ohm in parallel with 8 ohm. That is equal to minus 0.159. So as you can see, there is a drastic reduction in the voltage gain. And instead of amplifying the signal, it is actually attenuating it. So now in the second case, let us see what happens when we connect the emitter follower between the amplifier and the speaker. And in that case, let us find out the voltage gain. So in the second case, the overall circuit would look like this. So as you can see, here this emitter follower is connected between the amplifier and the speaker. And here this emitter follower is biased at the 5 mA using this ideal current source. So here let's say the voltage at this node is equal to Vx. So here to find the overall voltage gain, first of all we will find the ratio of Vx and the Vin, and then after we will find the ratio of the Vo and the Vx. And by multiplying these two terms, we can find the overall voltage gain. So here to find the ratio of Vx and the Vin, first of all we need to find the input impedance of this stage. So let's call this input impedance as the Zin2. Now for the emitter follower, we know that the input impedance is of the form R pi plus beta plus 1 times Re, right? But here instead of the emitter resistor there is a current source. And for the AC signal, this current source will act as an open circuit. Apart from that, here this coupling capacitor will also act as a short circuit. That means here between the emitter and the ground terminal there is a load of 8 ohm. That means in this case the expression of the input impedance can be given as R pi 2 plus beta plus 1 times RSP, where RSP is the impedance of the speaker. Now here we have been already given the value of beta as well as the RSP. So here the beta is 100 while the impedance of the speaker is equal to 8 ohm. So the only thing which we need to find is the R pi 2. Now we know that the R pi can be given as beta divided by Gm. So in this case this R pi 2 will be equal to beta divided by Gm2. That is equal to beta times Vt divided by Ic. Now here this emitter follower is biased at the 5 mA, and for the simplicity let us assume that this thermal voltage Vt is equal to 25 mV. That means R pi 2 is equal to beta times 25 mV divided by 5 mA, and the value of beta is equal to 100. That means this R pi 2 is equal to 500 ohm. So from this input impedance Z in 2 is equal to R pi 2 plus beta plus 1 times RSP. That is equal to 500 ohm plus 101 times 8 ohm. That is equal to 1308 ohm. So this input impedance Z in 2 will come in parallel with the 1 kilo ohm resistor. That means voltage Vx divided by Vin can be given as minus Gm times Rc parallel Z in 2. That is equal to minus 20 divided by 1000 times 1 kilo ohm in parallel with 1.3 kilo ohm. And if you calculate the value, then it is equal to minus 11.3. So as you can see, because of this emitter follower, there is a significant improvement in the gain of the common emitter stage. But here, to find the overall voltage gain, we also need to find the gain which is provided by the emitter follower. So we know that the gain of the emitter follower is of the form Re divided by 1 divided by Gm plus Re. So in this case, it would be equal to RSP divided by 1 divided by Gm2 plus RSP. Because as I said, here this current source will act as an open circuit. That means between the emitter and the ground, the resistance which is connected is the load only. That means for the given emitter follower, this is the expression of the voltage gain. Or in other words, it is equal to voltage Vout divided by Vx. That means Vout divided by Vx is equal to 8 ohm divided by 1 divided by Gm2 plus 8 ohm. And as we have seen, this 1 over Gm2 is equal to 5 ohm. That means voltage Vout divided by Vx is equal to 8 divided by 5 plus 8 ohm. That is equal to 0.615. So the overall voltage gain Vout divided by Vin is equal to voltage Vx divided by Vin times voltage Vout divided by Vx. That is equal to minus 11.3 times 0.615. That is roughly equal to minus 7. And still it is far better than the first case where the gain was minus 0.159. That means whenever the load impedance is very low, then it is always better to use the emitter follower as a buffer between the amplifier and the load. So I hope in this video you understood what is the emitter follower, and because of its high input impedance and the low output impedance, how it can be used as a buffer. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.